So here's the meme, or I guess just a mathematical joke. If we have a right angle triangle with side lengths 1 and I as shown, where I is the imaginary number, then by applying Pythagoras' theorem, we find that the length of the hypotenuse is 0. This is clearly nonsense, since the hypotenuse does not have 0 length. But humour me for a second. If we put this triangle on the complex plane, we could instead view this as the distance of the number 1 plus I from the origin. We can then define this distance for any complex number. For example, the distance of 1 to the origin is simply plus 1, while the distance from I to the origin is minus 1. This can be extended to any complex number. For example, 2 plus 3i, its distance from the origin is minus 5. And if we take an arbitrary complex number, x plus ti, its distance from the origin is minus t squared plus x squared. And actually, once we have this distance function, we can forget that we've been using imaginary numbers, and just think of coordinates tx for two-dimensional space with this notion of distance. Okay, you might be worried that this is actually distance squared, but it's conceptually much simpler to work with this squared distance, and we won't miss out on anything by doing this. But we already have a perfectly good notion of distance in the complex plane, the modulus. This is the same as the usual notion of distance in 2D space, known as Euclidean distance. Euclidean distance doesn't give weird results, like having a distance squared which is 0 or even negative. To distinguish between the Euclidean distance and our weird new notion of distance, we'll call this new distance the pseudo-distance. Also, to distinguish between these two ideas of distance, we'll use coordinates x and y when talking about Euclidean distance, and coordinates x and t when talking about pseudo-distance. We'll plot these on the same axes, but the x-axis is always the horizontal one. Now, one thing we can do is compare the idea of surfaces of constant distance away from the origin. For Euclidean distance, this is a circle. For pseudo-distance, instead we get a hyperbola. Now, returning to circles, we can rescale the circle, and by doing this we can get circles of any radius except for the degenerate 0 radius case. By contrast, by rescaling the hyperbola, which has negative pseudo-distance, we can only get hyperbolae which also have negative pseudo-distance. But we can just as well consider hyperbolae which have positive pseudo-distance. So in contrast to Euclidean distance, where there's just one type of circle up to rescalings, we get two different kinds of hyperbolae up to rescaling. Here the degenerate case is also more interesting. Instead of a single point, we get two intersecting lines. So we've built up some theory for the pseudo-distance, but does the pseudo-distance actually have a use? And the answer is yeah, or at least according to Einstein it is. The space of points Tx models spacetime in one spatial dimension. We sometimes refer to this as 1 plus 1 dimensional spacetime, for one time dimension and one space dimension. The choice of t for the coordinate was no coincidence. The points of spacetime are called events. The pseudo-distance turns out to be the invariant notion of distance between 2 points in spacetime. If we have two observers, Alice and Bob, Alice might see the event at xa, ta in her coordinates, while Bob sees the same event at xb, tb, and in general these need not agree. But the pseudo-distance must agree. We'd like to understand symmetries of spacetime. As a warm-up, let's return to Euclidean distance and first look at the symmetries of 2D space. Symmetries are transformations that preserve our notion of distance. We'll also ask that they preserve the origin, which removes translations, and to preserve our idea of anti-clockwiseness, which removes reflections. All that's left is rotations. An idea that can help us visualize these rotations is to restrict to a smaller subset of our whole space, which is nicely behaved under symmetries. But we've already looked at precisely such a subset. Since symmetries preserve distance, then surfaces of constant distance must be preserved. Then we can look purely at the action of a rotation on a circle, and then recover the action on the full space. And while we're in Euclidean space, I should point out the fact that Alice and Bob seeing the event in different places should not have been weird at all. The analog for Euclidean space is that if I see an object at xy and rotate, then I see it at a different point xr, yr, but its distance from me stays the same. Also here I rotated clockwise, so relative to me the object rotates anti-clockwise. Now turning to 1 plus 1 dimensional spacetime, instead of rotations we instead get what are known as hyperbolic rotations, and we can look purely at how they act on our surfaces of constant pseudo-distance. We saw that it wasn't weird that Alice and Bob didn't agree on where the events were located, but what might be surprising is why Alice and Bob don't agree, and it's because they're travelling at different velocities relative to one another. In relativity, we say Bob is boosted relative to Alice. Equivalently, if I accelerate on the spot, then I'd see the spacetime around me hyperbolically rotate in a continuous way. And notice that if I accelerate in the positive x direction, then relative to me, I see spacetime getting boosted in the negative x direction. And there's one last idea that we'll use, but in one spatial dimension it's a bit silly. Nevertheless, we can still define the idea. Firstly, the points of spacetime that have zero pseudo-distance are known as the light cone. Now if we take the plane t equals 1, then the points where this plane intersects the light cone are known as the celestial sphere. The sphere is the set of points which are 1 away from the origin, and in one dimension this is just the 2 points, plus or minus 1. Then I apply a transformation in 2 steps. First, I apply a hyperbolic rotation to these 2 points, but they don't necessarily stay on the original celestial sphere. So I can recover the sphere by rescaling the vectors back to t equals 1. Through this 2-step process, we've recovered the celestial sphere, but the one spatial dimension case is silly because whatever hyperbolic rotation I apply, the celestial sphere doesn't change. Of course, you've probably noticed that we don't live in one spatial dimension, we live in 3. But let's take a diversion through 1 plus 2-dimensional spacetime, or spacetime according to flatlanders. But if we rewrite the pseudo-distance in terms of spatial radius, then we can quickly find the surfaces of constant pseudo-distance, because we can just rotate our previous results around the time axes. If we rotate the hyperboloid of positive pseudo-distance, the 2 hyperboloids in 1D join together to form a 1-sheeted hyperboloid. But if we rotate the hyperboloid with negative pseudo-distance, we get a 2-sheeted hyperboloid. And the light cone really becomes a cone, or rather a double cone, but we get a single cone if we restrict to the points with positive t coordinate. And again, we can construct the celestial sphere by intersecting the light cone with the plane t equals 1. And for flatlanders, I guess it's really a celestial circle. Let's apply a hyperbolic rotation in the x direction. It preserves the light cone, and just as before, we need to rescale the celestial circle. And by doing this, we've seen that the points, or stars, have accumulated in the direction that we boosted in. And this is the perspective of a flatlander accelerating in the negative x direction. Relative to them, spacetime's getting boosted in the positive x direction. And this isn't the only symmetry. We can just as well boost in the y direction, and we can also do standard rotation, which leaves t unchanged. And there's a precise mathematical sense in which just these 3 types of symmetry can generate all the symmetries of 1 plus 2 spacetime. We're now ready to tackle the spacetime that we live in, 1 plus 3 spacetime. So let's draw out the sphere and add some stars. Just as before, the action on the celestial sphere happens in 2 steps. We apply a boost, we boost in the negative z direction, and just as with the celestial circle, the sphere gets distorted. So we rescale and the stars accumulate at the bottom of the sphere. And this actually corresponds to acceleration in the positive z direction, so once again the stars are accumulating opposite to the direction that you're accelerating in. And that's it, that's how you can see with your own eyes a spacetime symmetry. But in addition, there's also the rotational symmetries, and we can boost or rotate about any one of the x, y, or z axes. And in total, this gives 6 symmetries, which generate all the symmetries of 1 plus 3 spacetime. So in some sense, we can visualize all spacetime symmetries. But even though these generate all possible symmetries, there can be complicated mixing. For example, if we boost in one direction and then rotate in a different direction. I wanted to close out by saying there's a second part to this story which I wanted to tell. Surprisingly, there's another lens through which we can view spacetime symmetries, and this is through functions on the complex plane. For a taste, if we project the sphere onto the plane in the right way, then a boost in the z direction becomes a rescaling of the complex plane. And in fact, all spacetime symmetries can be understood as a complex transformation, or to be more precise, a specific family of complex transformations, the Möbius maps. Sorry, I mean Möbius maps. Which I find pretty crazy, but I think it'll need its own video to do it justice. So thanks for watching, hope you enjoyed the video, and I'll see you next time. Bye.